Good morning, ma'am. This is exactly 10.
Sure.
Yeah,
Good
okay,
morning.
fine.
Good
Yeah,
morning,
good morning.
everyone. Good
Okay,
morning to those who joined a couple
okay,
of
ma'am.
minutes ago.
Okay, ma'am, let me introduce, then we'll start.
Sure.
Yeah. Okay, very good morning to one and all. You're most welcome for the session 7 for the FDP. Uh, the latest technological developments for system on chip application. So already you have already discussed 6 sessions, concluding the particular remarks from the industry and the research persons. So today we have the particular research persons from her busy schedules, Professor Dr. Mariam Soejai Vagini. So Professor Mariam ma'am received the MS and PhD degree in electrical engineering from Sarifa University of Technology, Tehran in 1991 and 1999 respectively. She worked for more than 2 years in industry on the design of analog ICs. In 2001, she joined the Department of Electrical Engineering, IIT Bombay, Mumbai, India. Doctoral fellow, currently a professor. She has authored or co-authored close to peer-reviewed international journal and conference papers. She is the inventor or co-inventor of 6 granted.
Sorry, I interrupt. I think the 300 is missing. That's okay.
Okay, okay.
You're right. Close to peer reviewed. It looks like the papers are not peer reviewed.
Okay,
So
ma'am.
close
Sorry,
to
ma'am.
300 peer
Okay,
reviewed.
okay. Yeah, from this, okay. It's close to 300 peer reviewed fine. She is the inventor and co-inventor of 6 granted US patents, 6 granted Indian patents, and 4 more field patent applications. For
40.
which, yeah, 40 more field patent applications. Her research areas span from devices and sensors to the integrated instrumentation circuits and sensor systems and energy harvesting circuits and systems and analog mixed signal RF design for emerging applications. He has served as in the technical program committee of several IEEE conferences, including WSN track chair in IEEE Sensor Conference 2018 and 2019. She has a TPC
Sorry,
member of,
sorry. Somebody is talking in the background.
yeah, not clear. She was a TPC member of IEEE ASC from 2009 to 2014 and the track chair, analog mixed signal RF 5G, and invited speaker in International VLSIRD Conference 2019. She is the recipient or joint recipient of 15 awards, of which the recent award is Qualcomm Faculty Award 2021. She is Tata Trust Chair Professor in Frugal Engineering at IIT Bombay. So thank you very much for your biography, ma'am, and it is really impressive. So now you can start your session, ma'am. Like to ma'am.
Okay, thank you. Thank you for the introduction. And it's my pleasure to be in this program with all faculty members, all colleagues, and give you 2 or 3 examples of the research which is done in my group. And the main reason is because we are all faculty and we can learn from each other. And also to share our experience with you, and feel free to interrupt me even at the middle of the talk. In fact, I prefer to be interrupted because then the session becomes interactive and not, kind of one-way communication, which will not work. All of us are teachers, we know that. So how to interact with the students. So it's the same thing among us. So feel free, I will not be disturbed. Feel free to interrupt and ask questions, no issue. So I'm going to share my screen. Let me know if you can see my screen.
Sure, ma'am. You can say.
So you should be able to see my presentation.
Yeah, ma'am.
Okay, and I go to full screen mode. Let me
Yes.
know
Sure.
if it
Ma'am,
is.
for 1 minute, you can on your camera so that you can take a photo. Then you can off your camera, if possible.
Okay, sure.
Yeah.
So then I have to come out of the screen sharing, or
No problem. It is okay. No, fine. You can
which
on.
screen sharing?
Is it okay, ma'am?
Yeah, sure, no problem. So I'm turning on my
Yeah.
yeah, good morning again.
Yeah, good morning, ma'am. Now you can start, ma'am.
Okay. So I usually turn
Yeah,
off my camera because of the bandwidth limitations or any.
sure, ma'am. You
Yeah.
can off your camera.
Okay.
Thank you, ma'am.
Okay. So um, today the title of the talk is about importance of sensor interfacing and signal conditioning, ASIC. So I give you examples. So why are we talking about ASIC and not commercial ASICs? The reason is because the diversity of sensing technologies and sensors, along with the expansion of the IoT, IoE, has resulted a kind of quick developments in technologies and the requirements. And because of this, the commercial ICs, which are mostly for generic applications, will not be able to cope with this progress. And this progress also is not such a widespread everywhere. So you may find at different locations, at different applications, requirements, for which you need to have really interfacing and signal conditioning ASICs, which allow you to adjust and perform very well with respect to acquisition of the information and signals from sensors. Therefore, either we need to have a new way of developing generic ICs in the sense that less volume but more breadth, or another option would be to have something like FPGA in this area so that you can program it. But because these are all analog circuits, so the programming is not very straightforward. And that's the motivation for today's talk. So sensor systems have grown, and I'm sure all of you are quite familiar. In fact, I don't need to really present this slide. These are very well known to you. Applications are very well known. So this is not required. But what I want to talk about really here is just to tell you it is a time really that all of us can contribute to this technology and reach to the stage that the technology can be transferred to industry, even at 1% or 0.1%, and sometimes I hear 0.01% of the projects which are right now going on are converted to technologies which can be transferred to the industry. That will itself make a big difference. So, and these systems are growing faster and faster, and this growth is dependent on the infrastructure for networking, as we know, wireless networking. And that is the reason the IoT and IoE have become also another growing area in wireless communication and wireless systems. Of course, really in not everywhere we need to have everything wireless, but majority of the connections are wireless. So this is something also we need to keep in mind. In case we don't need wireless, fine. But practically, majority of the connections are wireless and need to be wireless. So this is also something I don't want to spend time on it, just to give an idea. These two are pillars, sensors and wireless communication infrastructure. Now, one more thing which comes the pillar is how to take signals from sensors. And that is the reason signal conditioning becomes a very important key module in this technology as well. So it's not only about sensor and the final system, it is also a part of the system, the main part of the system, which is how to really deal with the noise of the ambient and still extract the signals relatively accurate. So here, I give you an example, and this example is one of the ASICs, which is designed by one of my PhD scholars along with an MTech student, and then later on tested and then used for connection to the a sensor which is fabricated by another group of my collaborator. But here what I want to emphasize is that how we can move in this direction by defining the projects which can result in something different. And this is very interesting fact that I share with you. One of the examiners of the PhD scholar mentioned this statement that I'm wondering how this area, which seems to be saturated, you are able to publish in IEEE JSSC. So do we think that everything is expanding and technology is expanding, requirements are becoming more and more diverse and more variant? There is also an other side of the opinion which thinks that many of these technologies and requirements are already saturated. So therefore, we need to see that what is saturated and what is not saturated and has a scope. So this looks very kind of generic for you. Okay, signal conditioning for resistive sensors. You have heard a lot, right? And in fact, resistive sensors, which are used for so many applications, and they are fabricated using different technologies from very precise to disposal. And there is a wide range of products with wide range of prices and accuracies available. So makes it to look really saturated. But signal conditioning, specifically when we are talking about accuracy, and here the target is better than 100 ppm, is not still straightforward. What is the key block? Key block is instrumentation amplifier. Again, it looks like this research in instrumentation amplifier is saturated. It's not, because commercial instrumentation amplifiers have their generic requirement, generic specifications for a wide range of applications. But when it comes to custom design systems, it is very important and makes a difference if you have custom designs ICs as well. So let's start with the traditional instrumentation amplifiers. So one is trio-pump INA, right? This, I'm sure you are familiar. This is a very well-known structure. You can make this structure using discrete components, discrete op-amps, discrete resistors. You have this on given ICs. Variants of this configuration is available on commercial ICs, commercial INAs available on various semiconductor manufacturers. However, here, there is a point in any instrumentation amplifier which has to be considered, and it significantly determines its behavior and performance. I talked about how we can extract signal from a noisy environment. This is the first job of an INA. Therefore, the difference here with a conventional amplifier is conventional amplifier may not really need to extract signal from noise, but at the input of INA, signal to noise ratio is extremely poor, extremely poor. You may have a noise which can go peak to peak of several volts, and you have a signal which hardly goes to millivolt, peak to peak. So signal to noise ratio is extremely poor. But if you have a circuit which would be able to operate in a fully differential mode, in theory, you are able to extract millivolt signals from volt noise. However, the challenge comes exactly over here. To make a fully differential circuit and completely symmetric, you need to have very well matched elements. The amount of mismatch you have between the corresponding elements, here are the two op-amps, and 2 resistors will define exactly how well the INA is able to extract the information from a noisy environment. And that is where we can define how accurate it could be, or eventually starting with sensitivity, and we'll reach to accuracy later, but these two are connected. In fact, better sensitivity comes with better accuracy. How sensitive it can be and how accurate it can be. So therefore, this matching is very important. How it is taken care in industry? In industry, they have various techniques which are relatively expensive techniques, but because the volume of the production is high, they are able to manage it. That is laser trimming, for example, to make the transistors exactly resistors matched, and that is done one by one for each and every fabricated circuit on the silicon die. There is another popular configuration of the INA, which is also fully differential. It completely blocks the DC. This is very useful in the techniques when you don't have the DC level, which is compatible with the tolerable DC levels of the circuit. So it completely blocks because it's capacitive based. Here, you block the DC eventually, and you are controlling it by op-amp, but still the DC here is dependent on the op-amp. Range of the common mode range at the input of the op-amp. So this is the better configuration with respect to that. But here, however, you have so many components to be matched. Here, the configuration was developed in such a way that only 2 resistors and 2 op-amps have to be matched. But here you have to match 2 pairs of capacitors. And if you don't match them well, and on top of that, the input capacitance of the op-amp is not taken care well, actually equivalent noise at the input of the INA will increase. So one of the problems, therefore, is the conversion of common mode signals to differential, which comes with how precisely this circuit is able to operate in fully differential mode, which is eventually represented by common mode to differential mode conversion. It's a particular type of common mode rejection ratio, which is a performance parameter. And that will define how small the differential input could be. Because if you have a very low CMRR and common mode is very high, you will get a very high differential output, eventually differential mode signal, which is converted to single-ended here at the output, and that becomes comparable with what you get from the actual output of the sensor, and therefore signal to noise ratio at the output of the INA also will be low, and it will not allow you to extract signals well. One of the techniques which have become very popular, and in fact, when I started, in the second phase of my postdoc, in fact, at that time, I started using this technique. At that time, this technique was being used mainly in bipolar technologies, and it had paved the way into CMOS technology, but it was not being used very significantly. As a part of my second phase of postdoc, in fact, I designed an IC, and it was fabricated, tested, and we made a system using that. And in fact, the same design, TI showed interest to acquire the IP. So I showed that with current balancing technique, which is shown in this slide, it is possible not only to get good performance, but also, which is already known, it is possible to improve the power dissipation a lot and reduce it really very low, which is important for extremely multi-channel sensing applications. So when you need many channels, so it's very important the power dissipation of each channel to be controlled. So the technique tries to get rid of the problem of matching. So by eventually converting the input differential voltage into the current, mirror the current, and then convert it back to the differential voltage. So here you don't need to match elements. You have the gain, which is defined by the ratio of resistors and ratio of currents. If the mirroring current ratio is 1, gain is defined by ratio of resistors. And on the chip, even if you have process variations, ratio of resistors with the first order of approximation is almost independent of, or much less dependent of, the process variations as compared to a single resistor. And you know that one of the problems with passive element in the current CMOS technologies is the variability. You may get around 20 to 30% variability across different dies, which makes it very difficult to rely on a single value of the resistor for the design. And that's why ratio, always designs which are ratio based are important. And in this project, we have also used everything in ratio mode. So here I have just summarized what I told you, comparison of 3 different topologies and pros and cons of each one of them. So therefore, we start with the current mode INA or current balancing INA. Okay, so which we give us all in one. Whatever we don't have in the other 2 configurations, we get it over here. Before moving further, I want to talk about another technique also, which is very important for noise reduction. So you know that in most of the sensors, the actual frequency of operation may not be very high. We are talking about low frequency operation. When I say low frequency, means it could be below hertz, below 1 hertz, in the range of millihertz, could be hertz, could be hundreds of hertz, and could reach to kilohertz. So this is what we define here as low frequency. So now if we are talking about this kind of signals and this kind of range of frequency, so the question is, what about the internal noise of devices? We talked about only external noise to be very well blocked by the system. But what about the internal noise? If you are working with low frequency, at the low frequency, there is a big challenge, and that's the flicker noise, which is specific to CMOS technology. Flicker noise is about defects at the interface of the oxide and the channel of the MOSFET. And these defects, and though of course technologies over time have improved this defects issue and dangling bonds, but naturally happens because it's an interface between 2 different types of crystals. So therefore, these dangling bonds results in some energy eventually bands which can trap carriers. And then carriers are trapped and then released. So this mechanism is a low frequency mechanism. So it results in some kind of random behavior and random fluctuations on the current, which is passing through the channel. And therefore, it is a noise. And it is low frequency. As you reduce the frequency further and further, when you go from kilohertz to hertz and from hertz to millihertz, this power spectral density of noise increases. So therefore, we have an internal noise problem which comes from device and technology, and we need to handle it. And therefore, there is another technique as well that also we have used a lot in our ICs that we have designed and fabricated, is the chopping technique, which is called chopping modulation. So what is this technique? This technique uses the concept which is also available in communication technologies and eventually modulation schemes. So even today, we have in the transmitters up conversion and in the receivers down conversion. So that is similar concept. Eventually, it says that, so okay, so you have an input voltage, a signal which is coming from sensor, and you have an INA, which is shown here with the symbol A, and an equivalent noise at the input of INA, which belongs to this INA or is produced by this INA. So you can separate these 2 sources in frequency band by up-converting the input signal to a higher frequency band as compared to the noise. And this is done by F mode, F modulation. So we modulate up-convert. This technique can be a simple multiplier. And this multiplier could be a simple multiplication by a square wave. And if we do by a square wave, which is relatively easy because it's like opening, closing switches, equivalent of a square wave. That's why it is called chopping. So then it will give us a very nice, simple, relatively simple method to actually multiply input by a square wave. Here on the right side, I'm showing you one of our own INAs and the chopped output of our own INA as an example. So this is a sine wave, which is chopped by a square wave on the chip. This is the chip actually we fabricated in 2012. But because of the shortage of time, I won't present it here. But it's very interesting to know that this chip was designed by 3 of my MTech students, only MTech. And it was fabricated and it was tested. And then they made a complete system using that. And they reported the results and they published the paper after they graduated. So this was a very interesting experience. And of course, this was eventually a continuation of what I had done already. But at that time on my chip, there was no chopper. And then we added the chopper and they also changed some of the parts of the design. So this is the way it looks like. So if you have a sine wave, you multiply, the signal looks like this at the output of the chopper. Okay, now you give it to INA. Therefore, now flicker noise is at low frequency and the signal has moved to higher frequency. How much higher depends on how far you want to go from corner frequency of the flicker noise. And it depends on the corner frequency of flicker noise. For example, modulation frequency could be 500 hertz, could be 1 kilohertz, could be 5 kilohertz, 10 kilohertz. So it depends on how well you want to attenuate noise and how much you can afford to increase this frequency. Because if you increase it too much, you will have problem with the switching noise. There is no free lunch. Always when we find a solution, we also create problems associated with that. So then that's, of course, more sense in analog design, because analog design is complex because of the many trade-offs across several performance parameters. But this signal is up-converted. So this is not original sine wave. You have to bring it back to the original sine wave. That is like demodulator. So you modulate, demodulate. That's why we have a chopper at the output of the circuit as well. And that's why you see the sine wave again produced at the output. But you see switching noise. So you see the switches which are used actually have the parasitic capacitors. And they can couple the clock to the output. So these are practical problems. It's always good to see practical problems well in advance. In theory, everything is fine. But it's very important to see these problems well in advance during the design. Mimic them properly in simulation. Mimic the practical issues in the simulation. Otherwise, simulations look very ideal. So I always tell my students, if you simulate a circuit which works very well, everything is nice at the output, know that your simulation has a problem. So your simulation should really show real problems. Okay, so here you see the spikes. So we need to remove these spikes. So I don't talk right now about it, but I just wanted to tell you this is one practical problem. However, this technique works because this issue of spikes also is resolved. So now you have the original signal. So you just put a filter here and then you would be able to remove the high frequency part, which is coming at frequency of F mode, 3F mode, 5F mode, which is shown over here. So these squares of red that you see are actually representative of the flicker noise. Flicker noise goes through one chopping. Input signal goes from 2 chopping stages. So therefore, it goes to modulation, demodulation, but the noise goes only goes through one modulation. Therefore, noise will be up-converted. The original signal will be back at low frequency. So now you put a filter. You see this filter, which is shown by a dotted line. So this filter eventually will give you only this gray color area of the noise power. Therefore, now the peak of the noise power will be attenuated. If you increase frequency, so F mode increases, you can see the area of the gray color further reduces. And that means that you are improving the signal to noise ratio, and that is what we want to do. That's why this technique also is a very popular technique. However, it has to be done very carefully. So what here we have on the chip itself is a spike removal filter. This spike removal filter takes advantage of a fact that we know when these spikes are happening. These spikes are synchronized with the clock when the switch is opened. So therefore, we know the phases. So what we do, we put a switch cap, a simple switch cap filter, where the switch cap is disconnected from this filter during this time, exactly during the time that rising edge happens, and a little before that and after that, this is open. Therefore, there is no spike transfer to the output. And the signal amplitude also is relatively higher here, because this is now around 100 millivolt. So I assume that, for example, we use this for ECG recording. So input could be 1 millivolt, 2 millivolt, and output now has reached to, say, 100. This is, of course, an example. So this is not ECG signal. For ECG, I'm saying that it is 1 millivolt, depending on the gain we choose for the 1 to 5 millivolt. For the decay, depending on the gain we choose for the INA, we can achieve the output. Suppose with a higher amplitude. For example, if the gain of INA is 20 and the input is 2 millivolts, so output becomes 40 millivolts. So this is not a fixed number. Okay, so then finally, after the spike removal filter, you actually get the original signal, and the green color shows the input of the INA. So it's information and amplified information. Here, our gain was 10. So therefore, input is 10 millivolt sine wave, output is 100 millivolt sine wave. And when your output increases, removal of the spikes also is easier as compared to the initial chopping, which is performed on the signals with a low amplitude. So now going to the resistive sensor. So now we know about the chopping technique. So here the purpose of the whole system was to make a fully automated system which can determine the range of the sensor automatically, which can calibrate itself automatically in a complete calibration loop, and then it starts the signal conditioning and acquisition. So this is the entire diagram of the system. The only point is this is not something new, right? This is what is known already. And we start from here. We start really from conventional techniques. We don't really reinvent the wheel, but we show that how we can make a better system with adding innovations to the conventional techniques, right? We don't design from scratch. So this is AC excitation. This is a half bridge, reference resistor and the sensor resistor, you know that. And then now we want to achieve a very high accuracy. And that is where frequency of modulation comes to the picture. We have two frequencies. One is the frequency of input exciting current. It's a square wave. We have also a modulation frequency for chopping. And here it is shown for the case that we have the modulation frequency 10 radian per second, 100 radian per second, and 1000 or 1 kiloradian per second. How much would be the delta R by R that can be eventually, which will be produced as an error? Eventually, this delta R by R is the measurement error, but this is from simulation. But just from simulation, show that what would be the effectively delta R by R as we specifically produce the sensor resistance. So at the low values, delta R by R is 1 ppm. At higher values, delta R by R reduces. But one thing which is very important is to notice that the effect of 1 kilohertz frequency, 1 kiloradian frequency. So 1 ppm remains here. Now, if we actually go to 1 kiloradian per second, now one of the problems is that actually it's reverse. No, sorry, yes. This is sensors resistance. This is calculated delta R by R. Okay, yeah. See, the actual delta R by R is 1 ppm. And this is the calculated delta R by R, means that how low we can go. So when we go with a very high modulation frequency, so we get the advantage of going with a very high frequency modulation, so we can achieve better accuracy, better SNR, so we expect to get better performance. Now, here, if we use the same frequency over here, the problem is we have parasitic capacitors. So therefore, there will be inaccuracy with respect to the parasitic capacitors. Therefore, we have two errors. One is delta R by R, which ideally can be measured. That's why it's very important to include effect of non-idealities. But as the resistor value increases and the parasitic values are increasing, so we will have more error with respect to measurement because parasitic capacitors come to the picture for a higher frequency of modulation. So there is a trade-off here. One is trade-off. This trade-off is due to parasitic capacitors when modulation frequency increases. So I talked about switching noise because of modulation frequency. Here, even parasitic capacitors create a problem. So now we solve this problem by going to two different... Sorry. Yes. Hello. Hello. Is there any question? Hello, anybody? Can you hear me? I cannot see the chat box. I'm in full screen mode. Okay, okay, thank you. Okay, so therefore here the problem is this. We cannot have really a high frequency for the current source. Would you please mute your mic? I request the organizer to mute everybody's mic.
All the participants are requested to mute yourself. Prapti, just mute yourself.
I think you can mute.
Yeah, I can.
You can mute.
Okay, ma'am. Prapti?
You can mute as an organizer if you go.
Okay, ma'am.
There is an option for mute all.
Okay, ma'am, you can start, ma'am.
Okay. Okay, so therefore the problem is if we use same modulation frequency and same for both of them and same frequency, use the modulation frequency and the square wave which is used for the current source to be same, we will have the trade-off between the effect of parasitic capacitors, which increases the error, and the impact of flicker noise. So therefore, this was eventually one of the aspects that Mehraj, who was the PhD scholar and worked on this project, had to manage. So what, therefore, we learn here is we can't have same modulation frequencies. So to take care of this noise error trade-off, we go with two modulation frequencies. And that will help us to get rid of this problem. And here also you can nicely see the effect. As you increase the modulation frequency, the gray area reduces, which means that you have less effective power of noise over the signal band, and therefore signal to noise ratio improves. To summarize, for in-band noise, which is flicker noise, we need high modulation frequency. To reduce errors due to parasitic capacitors, we need to have a small and low value of modulation frequency. So this is a clear trade-off. So this trade-off is handled by using two different frequencies. So therefore, now we have one frequency that we call it F mode, which is for signals which are injected at the input currents. And we have one more frequency that we call it now F chop, which is used for the actual chopping. So effectively two. And therefore, we need to have one more demodulator as well. So this means that we are effectively increasing the number of choppers. This is the side effect. But it is helpful because now at the input we have lower frequency, F mode is low, and F chop is high. But we have to produce two frequencies, and then we need to use more number of choppers. So this is the proposed technique, and then this helps us effectively to reduce really the effect of flicker noise by moving this chopping frequency to a very high value without being worried about the actual frequency of the signal, excitation signal, which is over here. So this became eventually very nice work, and this is the same thing. He shows that eventually how the noise floor reduces as compared to conventional technique. But one thing I want to show you is about this fully automated system. It's not about only ASIC, it's about the entire system. And we started with the conventional system, and then we came to the full-fledged with complete feedback system with an external controller and with all eventually internal calculations using the controller, including a moving average filter, and give feedback. So therefore, there is an adjustment for adjustment loop, feedback for controlling the value of current, because it, depending on the value of resistor, this current amplitude has to be adjusted. If the value of resistor is high, current should reduce, otherwise input goes beyond the common mode range of INA, the point I referred to that at the beginning. So therefore, the current values have to be adjusted automatically. We need also to have an idea of the range of the sensor to be able to adjust the digital potentiometer, which is used over here to generate the reference resistor. Difference between reference resistor and sensor resistor should not be very high, but they will not be exactly matched also. So this difference has to be measured and entered into the system so that the system knows the initial difference. So this is eventually, this difference tells us how accurate we can measure. That's why for the calibration, we need to have these two automatically operated adjustments to be done. One for the current source, which is this part with the control signal, and this is the switch control and auto programming control for the purpose of getting the range of the input resistance for coming from sensor, and also even measure the offset, which is at the input of INA. By the way, offset also nicely is taken care by the chopping, because offset also is a kind of inaccuracy or non-ideal effect which happens at low frequency. Even if it has drift, it's very slow. Therefore, it is eventually combined with the flicker noise, and both of them are reduced. Now, the whole calculation is done at the system level. Therefore, our system directly gives us delta R by R at the output. And what we can achieve depends on how much really voltage we can generate. That depends on the current and common mode range of INA. But effectively, that will define our sensitivity. So it is the current we are flowing into RS. So that is what we define as a sensitivity, and it is the sensitivity. Eventually, how much we can get the variation in the voltage with respect to the relative change at the input sensor, which is I multiplied by RS. Intuitively also, we know that if we increase the current or we have a higher value of resistor, so we will get better sensitivity. So now this system is fully automated and gives at the output delta R by R. And the gray color is the low noise ASIC that is designed. Now here you see an XOR. So actually the one innovative part over here is, so he used this XOR to reduce the number of choppers. Eventually he mixed the two frequencies to control the final chopper. And therefore we don't need really to have two choppers and two demodulators here. This was another interesting novelty. And this is the current source which are designed eventually to drive these sensors. These current sources are programmable. We have first coarse, and then medium, and then fine, to be able to adjust the values very well. And then we have made them programmable, so that by controlling the switches, we are able to generate the currents at the levels that we would like to get. Again, there is very important point about current mirroring. That current mirroring also is a problem because we solved the mismatch problem, but we have current mirroring problem in current balancing technique. But this can be taken care by using a technique which tries eventually keep the VDS of transistors same, the transistors which are used for the mirroring. So we have used this technique in this design. And finally, we got the entire INA configuration, which is shown over here. The range of the current is pretty wide. It starts from 0.1 microampere and goes till around 44 microampere. And this gives us a wide range of input resistors which can be measured. And this is another advantage of our technique and our system, which gives it advantage as compared to other systems. So here is the fabricated chip. You can see current source generators, which are relatively also big because we want to have very accurate current generation. That's why transistors with long channel length are used. And we have an internal op-amp to control the VDS, which is shown over here. And that is the reason we have relatively large area consumed for the current sources. There are digital blocks which are used for control and shift registers for entering the control input from the microcontroller because we are programming the circuit with respect to the current levels. And then I had a collaborator, so they made actually systems. They made the sensors, and then we used their sensors to eventually demonstrate the operation of the system. We have also compared it with a standard commercial LCR meter. And what we did is that we actually put a sensor. We measured the variation of delta R with the deflection of the sensor. So you know that there are various types of sensors, and one of them, which is also used, the technique used in cantilevers and strain sensors, is with the deflection, the effective resistance changes. So here, this is the delta R by R as a function of deflection. When deflection is more, delta R by R increases. So we have reached really to a very low value, which is clearly around 100 ppm, and in fact, practically goes below that as well. But they should compare the results with the LCR meter results. So this is eventually showing them how accurate we can go. And these are 3 different measurements which are repeated. So that, you know, we have always variability across measurements. This is also very important. When we show measured results, it's important to show really the 2 or 3, specifically when at least 2 or 3 measurements, because when we want to show how accurate the points could be close to each other. So quantitative information are given in the table. I will show you. And then this is actually the effect of parasitic capacitor. So now, because the frequency of current sources is very low, actually we use 100 Hertz, it's very low. So even with parasitic capacitor of picofarad range, 2-digit picofarad, say 50 picofarad, we were able to achieve the 100 ppm target accuracy, though we could also go below that, as I show you in the table. See, here we are comparing this work with other reported works. They are all fabricated measure. Our work also fabricated measure. I want to attract your attention to these important numbers. One is about the area. Even though we have consumed a lot of area because of the accuracy we needed, still it is relatively low area as compared to other reported works. The technology we have used is 180 nanometer technology. Other reported works go from wide range of 500 nanometer down to 65 nanometer. So we have compared it with different technologies as well. So it's 700 nanometer even here. So here one interesting point is about base resistance. Look, the range is from 1 kilo ohm to 500 kilo ohm. In fact, we can go below 1 kilo ohm also if we increase power. Excitation current range, as I told you, 100 nanoampere to around more than 40 microampere. It's a wide range. That's why we had that coarse, moderate, and fine. Now, because of this capability of going with a wide range of excitation current range, so this delta R by R that we report depends on the values. Therefore, we report the maximum delta R by R which can be measured, as well as minimum delta R by R. Minimum delta R by R and maximum eventually define the dynamic range of delta R by R which can be measured. I start from minimum. Minimum, actually, we showed that if we go with low levels of current and low values of resistor, we can go as low as 26 ppm, because effect of parasitic capacitors will reduce further. And if we go to high value of RS and increase the current, and if we go to high value or reduce current, we are able to reach to 72 ppm, which is still quite good. Means that though our target was 100 ppm, but practically we could reach below 100 ppm. So at low values of the resistor, we are able to achieve higher accuracy, better accuracy eventually, by using higher value of current. But higher value of RS, because we have to reduce the current, so naturally the accuracy gets affected, and the impact of the parasitics will show up further. So this was the range, and maximum values, of course, can go even beyond 100%. So for 10 kilo ohm, we can measure up to around 135% delta R by R. For the 500 kilo ohm, up to around 120%. Time to this wide range, eventually it is 3 orders of magnitude, 4 orders of magnitude change in the current. Practically, we can actually reach to higher values, up to 44. So it's completely programmable. It's a programmable sensitivity because it changes with the value of the base resistor. It's fully auto-calibrated, and these thermoelectric effects are taken care by applying an AC excitation, so DC drift will not have any impact. And parasitics are considered, so it is taking care of the parasitic capacitors. And because of all these advantages, we could get eventually a kind of unique set of specifications reported for the first time in the world. That's why we could publish it in IEEE, Journal of Solid State Circuits, in 2020. So this is the first, in fact, ASIC I want to show you. Of course, I know that we don't have much time, but I gave you one example of the ASIC just to summarize it. This is suitable for resistive sensors, even with parasitic capacitors. It's very important to always keep in mind there are non-idealities. It is fully auto-calibrated. Therefore, user doesn't really need to get into the calibration and be worried about to learn how to calibrate. And if you don't calibrate correctly, you will not get results correctly. Resolution is pretty high, and range of the measurement is pretty high. Now we know that it goes from a few kilo ohm up to 500 kilo ohm, and accuracy also is very high. So, and all of them come with 2 important innovation in the design. One is at the INA level, which is with respect to making very precise current sources, precise current mirroring, and comes also with the advantage of using 2 different chopping frequencies. And also comes, of course, with the advantage of adjusting the current according to the input value of the sensor, so that we are able to manage the common mode range of the INA. So I have the second ASIC as well, but I'm not sure that if we have enough time. I would prefer to elaborate more on this example rather than starting another example and quickly go through that. If you are interested, you please just read and go through the details of the work in this paper. Meraj actually was a dual degree student in MTech plus PhD. So he converted from MTech to PhD. And then he is right now a research associate in Glasgow University, UK. And yeah, and he graduated recently. Yeah, and of course, let me just skip these slides But what I want to show you, just acknowledgements, because everything comes with funding for fabrication. So therefore, the funding from fabrication comes from the projects with DST and METI, Government of India. And of course, our labs, Embedded System Lab and VLSI Lab. We have fabricated chip by SCL Chandigarh. This is to acknowledge their service and through SMDP program. And also we fabricate through Europractice. And yeah, collaborators. See, this is Professor Ateshwar was the collaborator who gave the strain sensors. This is fabricated by them. That's why another beauty of this paper was everything was fabricated by the research groups, and we were able to eventually demonstrate a kind of, you know, something which is very close to a full-fledged product. So this is the team. Of course, I didn't present what is done by Laxmisha and Adarsh and Ajay, but what I presented right now was Miraj and contribution from Surya, who was a MTech student working with Miraj, but he's currently in TI India. Thank you. So I can go back to the slides about this circuit so that if there is any question, I can take. Hello.
Yes, thank you, ma'am. Any questions from participant side? You can ask.
Hello, ma'am.
Yes, hi.
And you have chosen the op-amp based LNA.
Yes, op-amp based INA.
Now, what is the merit over the source degenerated, the inductor based LNA?
Okay, so that inductor based LNA is used for high frequency applications because that is where you are able to provide matching for maximum power transfer. So that is LNA. This is INA. So LNA is usually, that's why I don't use the word LNA. LNA is used for wireless, eventually domain or eventually wireless transceivers. When we say low noise amplifier, though we can also talk about low noise amplifier is low frequency, but this is called instrumentation amplifier. Low noise amplifier is LNA, and the inductor, the generative inductor is used for eventually making the input impedance to be almost real, because then you need to match 50 ohm with 50 ohm, because that is for maximum power transfer. In low frequency analog, we don't have the notion of maximum power transfer. We have actually the notion of the signal amplification, amplitude. Because here in RF domain, of course, at high frequencies, we don't have the luxury of handling parasitics. Therefore, everything is based on power, not based on signals. At low frequency, it is based on signals. Here we are talking about low frequency. That's why no inductor is used. At low frequencies, inductors are bulky, not attractive. But resistors and capacitors can be on cheap. That's why we try to avoid using any inductor.
Thank you, ma'am.
Welcome.
I'd like to request our participants to, if they have any further queries, to put upon the queries to ma'am, or else they can drop their queries in the chat box. Dear audience, do we have any further queries?
Okay, I ask one question. Which INA do you use? Have you worked with INAs? For example, do you know any commercial INA? Have you heard about, say, INA triple tree? INA 321. So have you worked with any of these configurations in the past? For example, tree op-amp INA?
No, ma'am.
Okay, so you don't also have any course that you teach which is about instrumentation amplifier, or at least a part of the work?
That is the undergraduate course actually, where the instrumentation amplifier is there.
Which course?
It is, madam, advanced electronic circuits.
Advanced electronic circuits. Okay, okay. So the INA is included in that course. So actually, it would be. I think that's a very useful course for the students.
Yes, ma'am.
Right? Practical circuits are explained. So I think, yeah, you can include. I don't know. Of course, not all of you are teaching that course. I understand, but you can eventually bring some aspects of also integrated ASICs. And eventually ASIC means integrated circuits. Of course, you can also talk about commercial INS, but if you are interested, you can a little also talk about INS and ASIC.
Ma'am, Dr. Raut is here.
Yes.
Ma'am, I have one doubt. Yeah, hi. Ma'am, in that discussion of the capacitive INA, in that case, we are using the 4-5 capacitors. So
Yes.
when we are discussing the post simulation or the any fabrication of that particular design, so that capacitors effects, that means any parastux extra or
Yes.
any the area minimization
Sure.
point of view, it will not
Yes.
affect. Yeah,
No,
yeah.
it will. See, actually, in fact, this INA also, this capacitive feedback INA also is reported in many ASIC papers. Specifically, this has application in neural recording. So brain, for example, EEG, brain signal acquisition, EEG signal acquisition, it blocks the DC completely. So therefore, it is practically used. There are even ICs which use this INA on the chip. So therefore, they actually need to take care of this Cin. Gain is defined by ratio of Ci and Cf. Therefore, they need to spend area to make these ICs if they don't want to make small ICs. So they actually, because you have to make this Ci relatively high. And if it is high enough, then effect of Cin will go away. Because see, if you look Ci and Cin, if you ground this Vin, Ci and Cin are in parallel. So therefore, by making Ci high enough, much more than Cin, effect of Cin will go away. That is exactly the rule of thumb they use. And therefore, they consume area. So this is really area consuming. But it uses one op-amp. Here, if you want to make an integrated version of this, you need 3 op-amps. So therefore, this though has less number of elements, but when it comes to the area, this also needs its own area if you want to put all 3 on the same chip. So therefore, you need to have 3 op-amps on the chip, and here you have 1 op-amp. But here instead, you have 2 pairs of capacitors, and you need to have these 2 resistors as well. Otherwise, you cannot make a DC bias around op-amp. So here you have 3 resistors. So less or more, both of them are area consuming. In fact, here in this configuration, we don't have any op-amp. Op-amps go away. So our design, for example, if you look, it doesn't have per se any op-amp. We have used an OTA over here. Yeah, no, we have it over here. This has occupied some area overall because we have also 3 of them. You noticed also area was high for this part of the circuit. But that is okay. I mean, actually area, though we also talk about area for multi-channel because area defines the price. But I believe that if there are good designs, that's why I always tell students, keep area as the last thing to be worried about. Have a good design with good specifications. It is worth to spend more area. It's okay. So that's why I personally believe we should not be so worried about area unless if it becomes unreasonably large And suppose you have an 18 channels, 16 channel system, 32 channel system, then it becomes unreasonably large. Otherwise, it's fine. So area is not really a problem. I think the main problem we need to be worried is the matching. In these two configurations, matching are issues between
Okay, ma'am.
elements.
Thank you, ma'am.
Yeah, welcome. Okay, so I stop sharing.
Any questions from the participants?
Somebody has raised. Okay,
No.
okay.
Hello, Asya ma'am, are you there?
Yes, sir. Actually, ma'am, I think we don't have any further questions.
Yes.
And thank you. I would like to show my immense gratitude to you, ma'am, for sparing your valuable time among us and having this informative session, delivering the informative ideas upon importance of sensor interfacing and signal conditioning with so many examples, and also the suggestion which you gave for introducing this INA in undergraduate subjects, AEC, definitely we will keep your advice in our mind, and definitely we will try to include that topic in the undergraduate subjects. Thank you so much for, thank you so much, ma'am, for sparing your time among us. Thank you so much.
You're most welcome. It was my pleasure.
Thank you,
Welcome, ma'am.
I will connect you offline, ma'am.
Okay, thank you. Thanks, Dr. All the best for all of you.
Yeah,
Bye.
thank you, ma'am.
Yeah, bye.
Bye, ma'am.
Bye, ma'am. Dear audience, soon we are going to have our next session. So just wait for some time, and the next session is going to be start, which will be delivered by Dr. Subhrojit Pradhan.